Good evening, everybody. 6 o'clock. So we are done with our theories, and this today, like today and next Monday, is going to be student-led discussion mostly. So I was looking at this discussion page, final exam review topics. I don't see anything from you, your request. So what should we discuss? Tell me, is there anything? Any question? Any concern? Anything you want to review with me? No? Yes? No? Maybe?
In chat, someone has something.
Oh, okay. Can we go over one problem regarding the floating point? So, yeah, we did something on the, I think, last to last class, that example. So you are, Christopher, are you looking something else other than that? Okay, we can go over that problem once more. Sure. So let's see. Okay. Okay, so here's a problem we did, right? Basically, it's what you need to do from the problem is to figure out the pattern, right? The word pattern. Here in this given snippet, right? It says that we are storing a word these and var2 and var1 and var2 we are storing this word, and these two command LWC1, it's basically reading from this memory location and getting that complete word into F1 and um reading from VAT2 to F2. So practically F1 and F2 are loaded with this pattern, right? And then we are adding them. F1, F2 are adding them and putting them in the F12. And the last one is saying that I am putting a system call code 2 on the V0, which basically means to print the floating point number following the bit pattern stored in F12. So here in this program, we are actually updating the F12 with the summation of these two floating point numbers. So main point here is to calculate the what is the floating point value we are loading onto these two registers, which is represented by these 2-bit pattern, 32-bit pattern. And they're all on IEEE format. So what we do, we basically look at this pattern, expand that into 32-bit, and separate them according to this IEEE format bit field. So we have like sign bit, and then 8-bit of exponent, biased exponent, and then rest of them are fraction point bit. So we have fraction point bit of 110, this pattern, and E is unsigned 128. This pattern is unsigned representation. So exponent is 128 with a sign bit pattern of 1. Now fraction bit pattern, if we have this one, we assume we are talking about 1 plus that bit pattern. So it is represented as 1 point the fraction part of it, okay? Always, that is by the IEEE format assumption. And this 1 this goes as a -1 to the power s. So this is the s. So if it was 0, then it would be like a 0, -1 to the power 0. Now it is -1 to the power 1, which is -1, multiplied by 1 point this fraction bit pattern, multiplied by 2 to the power this exponent minus this bias, constant bias, which is like 127. So in this case, it is like this multiplied by 2. So we know if we multiplied something with the power of 2, we basically move the floating point towards the right direction by that many power. So this is 2 to the power 1. So we move this floating point 1 position. So we get this bit pattern 11.10111111. And from that, we basically translate it into the decimal equivalent, which is like after 2 to the power 0, it becomes 2 to the power -1, then 2 to the power -2, 2 to the power -3, those bit position weight. And we calculate that using calculator and come up with this number, like this value. So that means this bit pattern is representing this value. Now, if we follow the same step for this bit pattern, we will come up with a value this, okay? And then it is simply a matter of adding them, these two bit pattern. So this is my result, and that's, since we are printing the result on the F12, that's going to be printed on the Mars terminal. Is that okay? Okay, Christopher says it's perfect. So anything else?
On that problem there, the program wants floating point addition of a single precision. What would be the difference if it was double precision?
So double precision would be, you will be dealing with a 64-bit. That means here, okay, let me share again. So in the case of LWC1, and you will see there is an, I think, what is that? What is that command? Just hold on. I forgot how to have the double word. Let me bring out the green sheet. Okay, so here's a MIPS green sheet. So your double word, is there anything special for the double word? Let's see. LD, yeah, load FP. So it would be LDC1. Okay, so in that case, you will be loading 64-bit on the successive registers. So 64-bit successive registers means F1, F2 would be loaded, or let me see, what's the, yeah, FRT and RT plus 1. And remember, we can only refer to the even register for the double word. Like we can refer to F0, F2, F4, because the odd register part, that 32-bit is used to store that 64-bit pattern. So all the double precision commands can refer to the even registers. So in that case, it will be like F0, F1. We cannot definitely do F1 there. Let's say F0, we are loading that var. And we have to consider from the memory that successive 64-bit, not 32-bit comes up, and then split them according to the double precision format. Okay, so remember, like we have this one, double precision format, at the second page. here. Double precision bias is 1023, and we have 52-bit of fraction, and exponent would be like double, right? It is like 50 is 10-bit. Is it 10-bit? Yeah. 10, 11, 52. No, it is 11-bit, right? 52, 53, 54. Yeah, it's 11-bit. This is 11-bit exponent. So you are dealing with the 11-bit unsigned with the fraction 50-bit, and then you apply this bias in the same way, exponent minus bias. So you compute the unsigned here, put it here, use the double precision bias there. So you have 2 to the power something, you express that, and then move that much amount on the fraction on the right hand side and compute it. So that would be the double precision steps.
That makes sense. Thank you.
Okay, what else?
Do you have a problem for exceptions and interrupt?
Not really. No. No, if you don't have any question, then we can actually stop tonight and to let you study for the finals, and hopefully next time we'll have more like questions and topics. Please put them on the final review topics. Let's quickly look at the SOTE SOLET status for your class. I see that 37%. I see 37% for your class. That means so far you secured 3.7 out of 10 on that assignment. So if the whole class 100% goes in, so it will be 10 points. So now it is like 3.7 so far. For example, my other class has 60% response, so they are already reached the 6-pointer there. So hopefully you achieve that as a class. Okay. All right, there is one more. Is there a study guide for the final? Hey, can someone please explain me what is a study guide? What you are looking for?
Usually it like covers just a broad outline of the topics that might be on the final.
Yeah, a final is everything. So everything is your study guide, and there is a practice final exam to tune up your timing on that exam paper. So you probably, so that's your study guide. Which module you should focus more? Everything. Remember, you have these 70 MCQ question. It will come from everywhere.
Could we review K-maps?
Yeah, sure. So anything specific or in general?
Just a problem would be fine.
Okay, sure. Why not? Let's say I have, let's see, let me share again. Okay, so here, how do we proceed? Okay, let's proceed from a K-map itself, right? So we know that let's have some function like 4-variable function. Okay. That's it. Now let's say So to draw the K-map, first of all, I need to have a 4x4 table. And then we put the indices of those row and column in a gray code. And let's say it's okay. So this is the K-map. Now, what is the corresponding SOP in a compact form? It would be like from this guy, it would be like sigma m. And let's, okay, we can actually index them, the boxes to make it easy. 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this would be sigma of 0. So we are looking at all the where the ones are. So 0, 1, 3, 5, 10, 12. 10, 12. And then we look at the don't care term where the don't care are. So it will be plus don't care is, don't care would be 2, 7, 8. 2, 7, 8. Right? Don't care is this. This is your SOP form. Now, what would be the, for example, equivalent POS? It would be sigma of max term. If we basically pick up all the blank spaces, okay, all the blank spaces there. So it become like 4, 6, 9, 11, 13, 14, 15, 4. So we have 4, 6, 9, 11, 13, 14, 15. Okay. And don't forget a don't care term. They would be the same. 2, 7, 8. Now, how about the prime implicants? What are the prime implicants here? So what we can see, we can make a maximized group using the X as this guy, and grouping this corner. Is there any other possibilities? No. Okay. So here in this case, I believe your PI and EPI essential prime implicants, they are the same. It would be sigma M 0, 1, 2, 3, sigma M 1, 3, 5, 7, then sigma M of 0, 2, 8, 10, and sigma M of 8, 12, right? So let's check if we have all covered the ones. So 0 is covered, 1 is covered, 3 is covered, 5 is covered, 12 is covered, 10 is covered. Okay, yeah. So then what would be my equation or expression? Optimized, it would be f of x, sorry, wx yz equals, let's look at the first one, which is w bar x bar, or then we have next group, this one, it would be constant w at 0 and constant z at 1. So w bar z. Then about these corner groups, among them x is constant at 0, so x bar, and z is constant at 0, z bar. And then for this guy, it would become like okay, constant is w, y bar, z bar. So that becomes your optimized expression for that function. Make sense?
Yep.
Okay, what else? Is there anything else? No? Okay, then let's stop tonight and go back to your study. Make sure you cover everything up. And again, everything is a part of the exam. Okay, especially the MCQ will come from everywhere. All right, good night.